When people ask me why I'm so obsessed with AI chips, I tell them it's because they're the real engines of the future, the hidden reactors powering everything from autonomous cars to humanoid robots to the systems that will eventually build cities on Mars. And when I first started thinking seriously about this, it became obvious that relying on conventional chip companies wasn't going to cut it. They're too slow, too comfortable, too stuck in an era where incremental improvement is considered innovation. And that's just not how you build a multi-planet civilization. So I said, fine, we'll build our own. And that's how this whole journey began. Staring at a whiteboard covered in neural network diagrams and realizing we needed hardware that didn't exist yet. Hardware that could train neural nets so big and so complex that current systems would buckle under the load. And that's where AI-5 came from. A chip designed with one purpose: accelerate intelligence faster than anyone thought possible. But the crazy part is that AI-5 is just the warm-up, the appetizer before the actual feast, because AI-6 is where things start to get truly wild. AI-6 isn't just a faster chip, it's a new kind of computational architecture, something designed from the ground up to handle autonomy at planetary scale. And I told the team that if we want millions of cars learning from each other in real time, if we want Optimus robots working in homes and factories, if we want training that used to require supercomputers to happen in a device the size of a shoebox, we need an architecture that treats compute like oxygen, constant, abundant, everywhere. And that means manufacturing at a level the world has never seen. So yes, we're building fabs that will outproduce every other chip maker combined. Not because we're trying to flex, but because the future literally can't happen without that scale. And once we get AI-6 into production, we go even bigger with AI-7, a chip designed to evolve models on the fly. A chip built for intelligence that adapts faster than humans can code. And this is where things get truly interesting, because if millions of robots and vehicles can share knowledge instantly, the entire world becomes a neural network. A global brain where every failure becomes a lesson, every action becomes data, and every hour of operation becomes training fuel. And while the world debates whether that's possible, we're already outlining AI-8, the first chip built specifically for Mars, radiation-hardened, self-healing, capable of running autonomous construction crews on another planet, while the nearest human supervisor is millions of kilometers away. And when I talk about this publicly, people assume I'm exaggerating, but I'm not. This is literally the plan. Compute is the bottleneck for everything. Robots, AI, self-driving, manufacturing, energy, space. And if we want to reach the future fast, we need to remove that bottleneck entirely. Build so much compute capacity that innovation becomes constrained only by imagination, not hardware. And honestly, that's what excites me the most. Not the chips themselves, but what they make possible. A world where labor is automated, transportation is autonomous, robots do the dangerous and boring jobs, humans focus on creativity and exploration, and the species expands outward instead of stagnating. And every step of that journey runs through these chips, these building blocks of intelligence, these tiny slabs of silicon that will shape the next 100 years. And sometimes when I'm walking through the lab late at night, seeing the prototypes glowing under the test rigs, I think to myself, this is it. This is the moment where the future branches, and we're the ones crazy enough to try and push it as far as it can go. And as we move deeper into this AI chip journey, I keep telling the team that what we're building isn't just hardware, it's the nervous system of an entirely new era. Because AI 6 was the moment we realized we could push boundaries far past what anyone assumed was physically possible. But AI 7 is where we stop thinking in terms of chips and start thinking in terms of living computational ecosystems, systems that aren't just executing code but absorbing information, adapting, refining, optimizing themselves like digital organisms. And I remember standing in the testing bay looking at the early AI 7 models running simulations that would have taken entire data centers just a few years ago, and now they're doing it faster than human intuition, faster than biology. And I said to the engineers, imagine when every Optimus robot runs this. Imagine when every Tesla in the fleet is essentially a mobile intelligence node plugged into a global learning system. Imagine a world where the edge device is actually smarter than the server used to be. And the crazy thing is, we're not imagining anymore, we're literally building it. Because once you create an architecture where data moves through the system like electricity through a conductor, the whole definition of AI performance changes, and at that point, you can't think small, you have to go full scale, megafabs, gigafabs, factories that operate like computational forges, turning raw silicon into intelligence at a rate that makes traditional chip manufacturing look like candle making. And when we were sketching out the production lines for these facilities, I told the team that if we do this right, the bottleneck won't be capacity, it'll be creativity, because we'll have so much compute that the question becomes, what do we build, not can we build it? And that's where AI 8 comes into play. This architecture designed from the first line of code to function in places where humans might not go for years, maybe decades. A chip that a rover, a robot on Mars could rely on completely, with self-checking circuits, radiation tolerance, autonomous learning, everything needed to run a colony before humans even arrive. And the moment that clicked for everyone was when I said, look, this isn't science fiction, it's infrastructure. The same way you need power plants or roads, you need compute. And if we want a thriving multi-planet species, we need to send intelligence ahead of us. And that intelligence starts here. With these chips we're designing right now. And sometimes people ask me if it feels overwhelming, but honestly, it feels inevitable. Like, we're uncovering something that was always possible, but nobody dared to try. Because once you push past the mindset of limitations, you realize the future is just an engineering problem, and that's the part I love. That moment where the impossible suddenly becomes a matter of design choices, manufacturing scale, and a team crazy enough to take it all the way. And as I watch the prototypes come online one by one, I can see that future forming not in theory, but in silicon, in circuitry, in the hum of machines that are literally building the next stage of human evolution. And as we push toward the edge of what these AI chips can do, I keep thinking about how strange it is that the future of civilization comes down to patterns etched into tiny wafers of silicon. Because when I walk through the clean rooms and watch the robotic arms position each wafer with sub-micron precision, I realize we're basically manufacturing intelligence the same way past civilizations forged steel or built engines, except this time the output isn't mechanical power but cognitive power, And that's why AI8 isn't the end, but the launch platform for something much more radical. Because once we can mass produce intelligence at scale, we can deploy autonomous systems anywhere. Oceans, deserts, deep underground, orbit, lunar bases, Martian outposts, and each of those systems learns, improves, and feeds back into the shared network like a distributed brain. And I tell the team that the reason we need this level of compute isn't to make smarter gadgets, it's to make smarter worlds. Entire environments that are self-managing, self-repairing, self-optimizing. And when people ask me why Tesla is building chips instead of letting NVIDIA or someone else handle it, I remind them that the future doesn't wait for supply chains, it doesn't pause for bureaucracy, and it definitely doesn't reward the companies too timid to scale. So yes, we're aiming to outproduce every major chip maker combined, not because of ego, but because the demand curve for intelligence is going straight up, and the world needs a supply curve that can match it. And when I explain that to governments and investors, they usually look at me like I'm exaggerating. But then I show them the models, the projections, the simulations of what happens when robots, vehicles, and infrastructure all operate in unified intelligence loops. And they suddenly understand the scale. They see why we need millions of AI6 and AI7 units, why AI8 has to be rugged enough to operate for decades without maintenance, why the factories we're building are closer to computational ecosystems than manufacturing plants, and the whole time I'm thinking about the moment these systems start running together. When millions of autonomous agents share insights continuously, accelerating each other like compounding interest, but for intelligence, and I know some people are scared of that, but to me it's just the next step in human evolution. Not replacing people, but amplifying them, giving us the tools to build faster, explore deeper, dream bigger, and expand farther than any generation before us. And sometimes, late at night when the labs are quiet, I'll stand in front of an active chip under thermal load, watching the lights shift and flicker across the board, and I'll think, this tiny slab of silicon might one day run a robot on Mars, or build cities on Earth with almost no human labor, or help cure diseases by analyzing more data than any researcher could hope to process. And that's when it hits me that we're not just designing hardware,